Welcome, ladies and gentlemen. May I have your attention, please? Thank you. Raise your hand if you didn't get a red mark today, the 24th. Very good. Okay, today our Bellwork focused on finding inverse relations in 3 different contexts. We found an inverse relation whether we're given an equation, like number 1, whether we're given a list of ordered pairs for the original relation, or finally a graph. Well, what I did is gave a space so we could look at each one in more detail and I'd have room. So everybody take a look at the first one. I'm going to be calling on you to help with our 4-step process to find an inverse algebraically. First, is the original a function, right? Is the original a function? Well, if we think back to middle school, right, what category of function is this graph? Well, it'll be a line where we have kind of that start value and then plus or minus your rate of change times x. And so if this is a line in general, that would look something like this. Does this original relation pass the vertical line test, Braden?
Yes.
Is it a function?
So yes.
Yes, absolutely. So our original is a function. It passes the vertical line test. Each input will produce exactly one output. So yes. Find the inverse. Okay, here we go. So I'll do first step. First step, rewrite with y equals instead of f of x equals. Okay, go ahead and tell the class then what I do procedurally as I go to find the inverse algebraically. What do I have to do next? Dakota? Absolutely. Thank you. We'll go ahead and switch the position of x and y in my equation. So x equals 4 minus 3y. Now we'll go ahead and solve for that new y. Depending upon where that is, we're going to use a different series of inverse operations. It looks like our best first step would be subtract 4 from both sides. Then divide both sides by negative 3. So I'll get y equals x minus 4 all over negative 3. Now, depending upon if you were to look in the back of the textbook, for example, right, this negative 3 on bottom, they may grab that negative and distribute it through the top. It's kind of bad math manners to have that negative down sitting in the basement of a fraction. It's okay if you leave it like this. This is still correct. It's just I want you to be aware that you might see that negative redistributed through the top of the fraction. And that would change the sign on the negative 4 to a positive 4, the sign on the positive x to a negative x, and now the sign on the negative 3 to a positive 3. So you may see either one of these in the back. Now I want you to know that this, right, this particular relation, right, is going to be renamed, and we're going to rename it f inverse of x in accordance with our notation. So it looks like f inverse is given by 4 minus x all over 3. Great. So raise your hand if you got either one of these. If you got black, x minus 4 all over negative 3, or the rewrite. Way to go. Great. So our final question, thank you, hands down. Our final question is C, is the inverse a function? Well, again, this would be a linear function with slope negative 1/3 and y-intercept of positive 4/3. And so it turns out that yes, this would be, right, this would be a function because every input would be paired with one unique output, and it's a line, so it would pass the vertical line test because it's a slanted line. If I could try to draw that in there, I might be able to. So it might be something like that. There we go. So you can see that they are mirror images of one another when reflected about that diagonal y equals x, that identity function. And we've got that reflectional symmetry. Awesome. What questions do you guys have on number 1? Okay, be ready to share then your inverse of the original relation. Is the original a function, though, is our first question. So I'm scanning the problem. Go ahead and tell your partner whether the original is or is not a function, and why or why not. Okay, please share with the class what you and your partner decided and why. Okay, so is this a function? Why or why not? Katie and Braden.
It is because every x value has one.
Raise your hand if you agree with Katie. Yes, this is a function. Good, thank you, hands down, that's exactly right, Katie. Every x value, right, every x value is paired with one and only one output y value. So no inputs repeat, so yes, it is a function. Good, thank you. Find the inverse. Go ahead and share with the class the inverse next. So what am I going to have for the inverse? Mark?
It'd be 3, 2, 7, 5, 6, negative 1, 4, negative 2, 3.
Oh, we're just going to make it. Excellent, thank you. Okay, everybody, scan it. Go ahead and tell the class whether this is a function, whether the inverse relation is a function now. So what do you guys think of this one? Be ready. And what do you guys think of this one? Will and Casey?
Yes.
Yes, how come?
Because no inputs repeat.
Absolutely. So even though now we switch the coordinates, it appears none of the inputs repeat. Each input is paired with one unique output, and that's guaranteed if none of them repeat, because there's not a chance to be paired with more than one output. Nice job. And lastly, is the inverse a function? Is the inverse a function? Check. Done. Thank you. Casey, well, so we got a yes, yes. One to go. From the original, can we generate an inverse if we're given a graph? You bet your boots. But first, go ahead and tell the class, is the original a function? So the one you're looking at. So is the original function the one you're looking at? Heather and Marina? No, how come? So I agree that the horizontal line test can be used to tell whether or not something will be a function. But for letter A, I want to know if the original graph that we're looking at is a function. And so would I use the horizontal line test to see if the original is a function? Yeah, we use the vertical line test for the original. So we can answer A and C without finding any inverse. So thank you for bringing that up. Look at here, we've got our original. Our original passes the vertical line test, and so yes, the original passes the vertical line test. However, we can already tell whether or not the inverse will be a function before we even find it if we were to do the horizontal line test. So thank you for bringing that up. If we did the horizontal line test, does the original pass the horizontal line test, Heather? No. And so, is the inverse a function? No, the inverse won't be a function. Now I'm going to go ahead and use the same justification on the original. The original does not pass. Does not pass. And this time it's the horizontal line test, right? The horizontal line test can be applied to an original to tell in advance whether its inverse will be a function or not. All right, now let's go ahead and generate it. How can I do that? Very carefully. No, I'm just going to go ahead and get integer pairs by looking at the original, and then invert their x and y coordinates, much like we did with number 2. So here we go. Key point 0, 0 will correspond to 0, 0. 1, 1 will correspond to, well, 1, 1. 2, 4, however, will correspond to 4, comma 2. So 1, 2, 3, 4, comma 2. Negative 1, 1 will correspond to 1, negative 1. And negative 2, comma 4 will correspond to 4, comma negative 2. Let's take a minute and carefully connect those, and we'll get a picture of our inverse relation. And it looks like it's still a parabola. It's just a sideways opening parabola. Instead of opening up down like our parent function squaring function, this parabola opens to the right or to the left. So this one opens to the side. Awesome. Raise your hand if you had a picture that matched number 3. So who had that same kind of picture? You get key integer points with your pen or pencil tip, and then invert their x and y coordinates before plotting the new points and connect them. Nice work. What questions do you guys have about today's Bellwork? Awesome. Then let's go ahead and take care of our fire drill for first hour. So we will be having a fire drill. Our fire drill is tentatively planned today for around 9:40, so that'll be the tail end of our class. I just want to point out our fire drill procedure. So for us, we're going to go ahead and go to the right as we go out of the door. We're going to go to the right, down the hallway, and we're going to go down those stairs and then out the door. So we're not going to go down to the commons double stairs. We're not going to go into the main entrance. We're going to go down the hallway, past Mr. Akers, turn right. We're going to go down the stairwell and straight out, and then we're going to go all the way across the parking lot, all the way across the street, and then into where the sidewalk is by the track in the football field. Okay, so we keep going. We don't stop right at the doors. Does that make sense? Awesome. We'll have a chance, because I'll forget. All right, so I put this to remind me. I already did forget. So this is reminding me that we'll probably have a fire drill. Now, all that preparation, when it still sounds, it'll still scare me because I'll have forgotten that there's going to be a fire drill today. So I just want you guys to know in advance. We'll out the door, to the right, down, and then we'll keep going across the parking lot, across the street, and then to that sidewalk. Awesome. Thanks, you guys. All right, let's go ahead and make sure your name is on top of our Unit 8, Day 8 assignment. So assignment number 8 was the stapled packet. It had the matching. At this time, please make sure that your name is on the top. Give yourself credit for those you completed out of 26, please. No reading questions. So out of 26 in pencil, divided by 26, enter, multiply by 4, and then round your bring campus score to the nearest half point, 0 to 4. Make sure that's box nice and top on big. Or nice and big on top. And let's go ahead and check our answers. So pencils down, let's get our grading pens. And let's check our answers. Ready? Page 1, let's get to know our parent function. Ready? Left, right, 1, 2, 3, 4 would be B, binomial, D, decimal, 3 is A, algebra, 4, C, calculator. Next, 1, D, decimal, 2, A, algebra, 3, calculator, 4, B, binomial. Next, left, right, 1, D, decimal, 2, C, calculator, 3, B, Bernoulli, 4, A, algorithm. Next, 1, C, calculus, 2, D, decimal, 3, A, algebra, 4, B, binomial. For our sketch, we wanted to identify the parent function for the family. Number 1, that would be the absolute value function family. Absolute value function family. The parent function is shown in red, and that's just directly from your green sheet. And then the new function, it looks like the y-coordinates are going to be half as tall. That's that multiplier 1/2, makes them less steep, more gradual, shorter y-coordinates. How much shorter? Half as tall. That's what that half multiplier does to every single y-coordinate in your pairing. Parent function in the second one is the reciprocal function family. The negative flips, right? Flips across the x-axis, the original hyperbola branches in blue, now become the new hyperbola branches in green. So the negative reflects all those points across the x-axis. And so now you're in quadrant 2 and 4. So the new one is the green one in 2 and 4. Absolute value function. The 2 makes the arms twice as tall, twice as steep. So every y-coordinate for a given x-coordinate is twice as tall. And the negative flips it across the x-axis. So it's an upside down V shape, twice as tall. Fourth is the squaring function family. The original graph in blue, every y-coordinate is half as tall. And so this key point 1, 1 now is going to be paired with 1, 1/2, half as tall. This key point 2, 4, or negative 2, 4 will be paired with negative 2, 2. Look at half as tall. Half as tall as the y-coordinate because that multiplier out front of the function was 1/2. And we'll practice more of that today. Bless you. The reciprocal function, again, negative, again, that flips it across the x-axis. The new one is in green. The cubing function family, the negative flips it across the x-axis, and so the new one is in green. The square root function family, the negative flips the blue across the x-axis, the new one is in green. The inverse squaring function family, the 3 multiplier on top makes every y-coordinate 3 times as tall. So this key point 1, 1 is now going to be 1, 3. Look at that's 3 times as tall as the original. This key point 2, 1/4 is now going to be 2, 3/4. 3 times as tall as 1/4 is 3/4, and so on and so forth. The new one's in green. The parent was absolute value function. This one is half as tall. The arms are half as steep, so the new equation would be y equals 1/2 absolute value of x. And these are the trickiest because it's just our second day working with them. But this would be the correct answer. The parent function would be the inverse squaring function, 1/x², except this one was upside down Atari symbol. And down, down, in quadrants 3 and 4. Our parent was a square root function family, but the arm was twice as tall. The y-coordinates were twice as tall. And so instead of the key point 1, 1, it had 1, 2, twice as tall for the y-coordinate. Instead of 4, 2, it had 4, 4, twice as tall. So y equals 2 times root x. And lastly, a constant function, y equals k. This particular function, the constant function, the y-coordinates on every single point on that blue graph was -4, so y equals -4. It's kind of hard to see on the printout because it's black and white. It should be y equals -4. Okay, at this time, let's go ahead and give yourself an accuracy fraction out of 26. About how many did you get right in pen and circle it? Make sure your infinite gamma score is in pencil boxed. Big on top, make sure your name's on the front page. Make sure your name's on the front page. Let's go ahead and pass from the back to the front, and I'll go ahead and pause the recording while we discuss our quizzes. Wonderful, ladies and gentlemen. Okay, so by the end of today's class period, we're going to be able to graph piecewise-defined functions. We're also going to write the equation of a piecewise-defined function given its graph. And so a 2-part objective today, we're going to define piecewise functions, and then we're going to be able to graph piecewise-defined functions, and we'll do it both ways. But first, we're going to have our first round of function calisthenics. And so before we get going, I want you to listen carefully to the setup. I'm going to pull over the file. And we're going to be very careful. We're going to be very careful with our microphone. So, a quick refresher. Yes, Cody. Oh, Barrett, thank you so much. Appreciate that. I'm going to tell him that you were saying we should leave him out there. So, what we're going to do is think back to our parent function, right? F of x equals x, our identity function, and that was our identity function was our parent line that went through the origin at a 45-degree angle, right? Slope of 1 and y-intercept of 0. And so when k was positive, right, remember we had the same direction. We had the same direction graph, even if we changed the value of k. So long as it was positive, we had this increasing behavior. So what I'll do is I'll call that the same direction. Same direction. Versus when k was negative, what did that do? It flipped our behavior. We had the opposite behavior of our parent function. We now had decreasing behavior, so we had the opposite direction. It's all right. We're just reminding. We're reminding ourselves from our green sheet. When k was large, what did that do to my parent function? Y equals x. Well, if it was y equals 3x, then it got steeper, right? The y-coordinates got taller. And so we have taller y-coordinates, a steeper line.
Wait, you did this.
Pardon?
Absolute value?
This one, the absolute value of k, meaning the multiplier could be positive or negative, but big, like 2, 3, or negative 3. So still taller y coordinates, right? Still taller y coordinates, steeper line. But no, absolutely right. And then the absolute value of k was small. That's like a fraction in between 0 and 1, like 1/2. What did that do to your line? It made it more gradual. So you're going to have to show that with your bodies. You're going to have to show a more gradually sloped line. So that was shorter y coordinates and a more gradual line. Good job. Next up, we had y equals x squared. And so recall your parent function from your green sheet, our squaring function. Our parent function was our right side up parabola. Our right side up parabola. When k was positive, the steepness of the arms might have changed because I'd get taller y coordinates or shorter y coordinates. However, if ever k was positive, we had the same orientation, a right side up u. So in just a minute, right, when you model that, positive k values are always going to be right side up, bowl shapes. Negative k values will be upside down bowl shapes. Large values of k, what's that going to do to your u? Again, taller y coordinates, right, means you have steeper arms. If k is small, then we've still got right side up or upside down, but we've got shorter y coordinates. We've got a more gradually sloped arms, and so we're going to have kind of a wider bowl shape. We'll call that shorter y coordinates again. So taller y coordinates, steeper arms. And shorter y coordinates, the arms are less steep. Okay, and now it's time for your soon-to-be favorite game. No, Brayden, no. Function calisthenics. Oh, function calisthenics. So I'm excited about that. Let's go ahead and everybody, we're going to get up around the room and we're going to make one great big circle around the perimeter, and you're going to have to get close to me. So just leave space in the front board, no? So Logan, Will, start here. That way we'll leave the smart board so we can all see. Come close to me a little bit. Spread out a little bit so you don't poke your neighbor in the eye. Come more this way. Fill it in, Katie, come closer to Margot. There you go. Yep. So fill in so you guys spread out because I don't want you guys hit each other in the eye. Everybody good? Everybody have a little space? Okay, if you need to do the stutter step forward and back, that's fine, so that when you do your arms, you don't hit Luke in the eye, right? So if you need to do a little forward back, that's great. Good job, Brady. We have followed directions. So let's go ahead and take a look. We're going to model behavior of the function, and we're not going to put our arms up. We're not going to put our arms up until I say go. That way we don't spoil the party for everyone. So wait until I say go. Everybody think about what y equals x squared looks like in general. Y equals x squared. In just a minute, you're going to show me with your body, but you're going to wait until I say go. Get ready, and go. Y equals x squared. Check in with the computer. Everybody wins. All right. That was a warm-up. Get ready. Think about what this looks like. The thing is that you're going to make the graph. Guys, you're going to make the graph for the person across the room, like on their graphing calculator. So you have to think about what arm is up. And so for me, I'm going to be putting my left arm up so that Tyler sees the picture on his calculator of a positively sloped line. You see that? So you're making the graph for the other people to see. Dakota, do you see? I'm making a positively sloped line for you, which means that if you're going to make a positively sloped line for me, what arm do you have to put up? Your left arm, because you're making the picture. Go ahead and do it. Yeah, everybody left arm up. Let's check with the, keep it up. Did you make that? Yes, you did. So you got to get that straight. Okay, shake it out. Woo. That was tough. Okay, so those are our warm-ups. Get ready. Don't do it until I say go. Y equals negative x. We just had our left hand up when we were doing y equals positive x. So don't do it yet, but think about how you're going to have to change your graph to model y equals negative x. Get ready and go. Right hand up. Waggle it. Right hand up. Good job. And the computer says you are correct. Good job. Get ready. Y equals 3x. And so that's a positive 3x. Right? So we're back to the whole left hand right thing, but we need to show the 3 and what effect that's going to have on the steepness of your line. So wait until I say go. Get ready, go. Oh, nice and steep, right? Gosh darn it. Look at that. I can see it across the room because Braden had it perfectly. Do you guys see that? Steep, good job. Next, y equals negative 2/3 x. Get ready, y equals negative 2/3 x. Think about how you're going to show that with your arms. We've got negative, so think about what's going to be on top. And we've got a fraction in between 0 and 1. Get ready. And go. Not quite as steep, right hand a little taller. Right hand a little taller. Waggle it, right hand a little taller. There you go, good job, and you win. Next, y equals 0.287x. Y equals 0.287x. Let's think about what that's going to look like. Get ready, and go. Very gradual, left a little bit taller, left a little bit higher, left a little bit higher. Good job, and arms down. There you go. Y equals negative 4x squared. Think about it. Don't do it. Think about it. Y equals negative 4x squared. Get ready. And go. Hold it. Hold it. Check it out. And you win. Shake it out. Good job. Good job. Y equals positive 1/2 x squared. Everybody look. Get ready. Don't do it yet. Positive 1/2 x squared. Get ready. Think about how you show that, and go. We're gradual, we're checking with the emulator. Oh, you win, good job. Y equals negative 13/2 x. Think about which arm. Y equals negative 13/2 x. Think about how you're going to show that. Wait, get ready, and go. Oh, tall right, tall right. Tall right, negative slope. Tall right. Tall right. Tall right. Let's see. Oh my gosh, that's steep. Y equals negative 3/11 x squared. I'm sorry, positive. Positive 3/11 x squared. Get ready. Think about how you're going to show that. Positive 3/11 x squared. Get ready. Don't do it. Get ready. And go. Oh, I'm so gradual because 3/11 is like not very large. See it? Good job, you guys. Almost there. Y equals negative 1/5 x. 1 to go. Y equals negative 1/5 x. 1 to go after this. Get ready. And go. Gradual flat. Negative 1/5. Right hand a little higher. Right hand a little higher. Hold it. Oh, there it is. Right hand a little higher. Good job. And last one. Y equals negative 2/9 x squared. Think about it. Don't do it. Think about it. Y equals negative 2/9 x squared. Get ready. And go. Upside down, a gradual curve. Hold it and check. You win. You guys are awesome. Congratulations. You survived round 1 of function calisthenics. Good work. Good work. And go back to your desk. Tomorrow's round 2.
Tomorrow?
Next class. Next class. Nice job, ladies and gentlemen. Okay. Thanks for playing along. I know that's a little bit different activity than you might be used to doing in your math classroom, but we will have another round. Yes, that's right. Stay tuned for round 2 next class period, where we're going to go ahead and add our reciprocal, right, with the branches, our hyperbola branches, and the inverse squaring with our Atari branches. And so we're going to be using our hands to model in which quadrant the given function lies. And so we've got that to look forward to and pull us through this weekend. What I want to do now is direct your attention back to our day 9 note sheet. So everybody find your day 9 note sheet. Bottom of Bellwork, consider the graph of y equals absolute value of x. And so we remember that as our parent function v shape, right? Our y equals absolute value of x is a parent function v shape. What I'd like for you to do is write a linear equation for the right side in blue of the graph that does not involve an absolute value. In other words, could we rewrite that blue portion of the graph in terms of one of your other parent functions? Well, for that segment, you certainly can. Look at your green sheet and find which function that most closely resembles besides absolute value. Don't say it out loud, just find it. And if you were just looking at the blue portion of the graph, which parent function does that portion most closely resemble? Ben?
Y equals X.
Yeah, y equals x. Looks like that side. So my parent function f of x equals x. Looks like the blue right side of that graph. In fact, we could do a transformation with this parent function, f of x equals x, in order to generate the left side. Write a linear equation for the left side of the graph that does not involve an absolute value. What k value would we have to put in front of my x term in order to create the green picture? Go ahead and tell the class when I call on you. Adam? A negative, right? A negative 1 in front of our x would create the green. So I'll go ahead and write f of x equals negative 1x. I'll just write negative x. That would produce the green portion of the graph. However, the blue portion, f of x equals x, this equation goes on forever. And in the picture, it only occurred when I was looking to the right of the y-axis. And so, this blue equation only applies when x is greater than or equal to 0. Then the blue equation creates that graph. And this green equation only applies if I'm looking to the left of the y-axis. That'll only apply if I'm looking when x is less than 0. Now, in this case, the or equal to could have gone on either of these function definitions because that they share the same point, 0, 0. And so it would have been okay to put a or equal to on this inequality or leave it on the top because they share the same point. It would still be a function. All right, you guys have just seen your first piecewise defined function. If a graph is described in pieces, like the blue piece and the green piece, the graph and function are called piecewise. The graph is a combination of several different curves. Each curve can be described by a function rule that has a restricted domain indicating where the curve starts and stops. So we'll be looking at little x windows, little intervals of x values where a particular rule applies, and break it up into different pieces. That's why it's called a piecewise function. Writing a function for a piecewise graph requires two things. One, writing the equation of each curve, that's the what, right? What function rule applies. And then two, indicating the domain for that piece. That's the where. For what x value windows does that piece apply? So, graphing a piecewise function requires graphing each curve for the indicated domain only. So let's go ahead and try some. So we're going to go ahead and try some now, right? Let's suppose that we're given a piecewise defined function. And they're easy to recognize because their function definition has this big cursive bracket, and then it has a different function rule for each piece of the graph. Take a look at this first one. F of x is given by x squared, but only for a particular window of x values. F of x is given by x, our identity function, our line, but only for a certain x values. And lastly, f of x is given by 2, a constant function. But again, only when you're looking at certain values of x. Let's go ahead and make this one together. So if I let f of x equal x squared, but only on the window from -1 to 1 for x values, that's not going to be the entire parabola. It's only going to be on this little window when x is in between -1 and 1. And so while my normal key points from your green sheet, everybody find it, my squaring function has 0, 0, -1, 1, -2, 4, 1, 1, and 2, 4, and has the parabola arms go on forever in both directions. We're only going to darken the piece of the parabola in between -1 and 1. Furthermore, because this is a strictly less than on the -1 value, I'm going to make an open circle and not fill in the point, versus the or equal to on the second one, I'm going to darken and fill in the point. And so there's our portion of the parabola, and I'm going to go ahead and fill in. I'm going to fill in the rightmost x value point, because the parabola does give that y value. It's because it's or equal to, but I'm going to make an open circle for that left side of the window because this is strictly an equality symbol on the -1. Everybody see it? There's our parabola in red, but only applied to that window of x value specified. Next up, our constant function. Our identity function, rather. Let's do that in blue. So I'll go ahead and do that in blue. The first one I did in red, there's my color coding scheme that looks like a little jelly belly. I'm hungry. I'm always hungry. Let's do our identity function in blue. What does that look like? Oh, our identity function is that line that goes through the origin at a 45-degree angle, right? Positive 1 slope, y-intercept of 0 goes on forever in both directions. However, we're only going to darken the piece of that when we're looking for the x values to the left in or equal to -1. And so I'm not going to fill in this entire line. Where am I going to fill in? I'm only going to fill in to the left of or equal to the x values, -1, and forever to the left. So I'm going to fill in here because it's or equal to, and I'm going to shade which direction? I'm going to go which direction? I'm going to only darken to the left. And I'll show that that goes on forever with an arrow. So our linear function is only darkened when x is less than or equal to -1. Last piece, Margot.
I have a question. Like with the open circle, closed circle, what if you have to have an open circle and closed circle on the same spot?
Then it's a filled in circle on your graph.
So
You just should know which definition is making it filled in, and that's based on which one has the or equal to.
do you have to do it in different colors? Or do you do it all in different?
No, you don't have to do it in different colors. I'm doing it in different colors so that we can see which piece applies, which function rule applies to which piece of the graph.
Okay, thanks.
You're welcome. Next, our final piece is given by the constant function, f of x equals 2. The constant function takes any input and pairs it with y equals 2. And so it's a horizontal line, right, where y coordinates on the point are all the same too. However, that would go all the way across forever in both directions if I did my normal graph. In this case, it's a piecewise-defined function. Y equals 2, right, is my constant function, but I'm only going to darken those points when x is to the right of x equals 1. So where will I darken this? I'll only darken it over here, to the right of x equals 1. However, because it's a strictly, I won't fill in this point. I'll leave it as an open circle and darken to the right. In this way, we've created our piecewise-defined function. Would it be helpful if I erase those extra dots now? So we put them there to see where the graph goes, and then we only darken the domain restriction part. So now I'm going to get rid of these extras. There we go. Do you see the pieces? So the what is the function rule, right, that creates the graph, and the where is the domain restriction. You can see that we're squaring, but only in between x is -1 and 1. We're the parent function, the identity function, but only to the left of x equals -1, and then we're a constant function, but only to the right of 1. That's how we decide where to fill in our function. Let's try another. In this case, f of x is given by the square root of x, the absolute value of x, and the cubing function, x cubed. However, each of these pieces applies on a different window of x values. So let's look at the first one. I'll do that in red. Our first piece is given by y equals the square root of x. Y equals square root of x. Everybody find it on your green sheet. Everybody find it on your green sheet. That has key points 0, 0, 1, 1, 4, 2, 9, 3, and so on and so forth. It's half a parabola arm, right, that opens out to the right. This particular graph is going to apply when x is greater than or equal to 0, which is exactly the domain of my original. So I'm going to fill in all of this. Is this going to be open or closed? Well, at 0, 0, it'll be closed because that has an or equal to on my domain restriction. So this will be filled in and everywhere to the right. I'll show an arrow, right? I'll put an arrow to show that it goes on forever. My absolute value V in blue would be the V from our green sheet, forever and ever in both directions. However, because this is a piecewise defined function, we're only going to darken the portion of the graph when x is in between -2 and 0. because it's a strictly on the 0, this would be an open circle for blue. However, we've already filled it in for red, right? You see? So we've already filled it in for red. So this is a filled in point because of the red. We'll go ahead and draw until -2, and then because it was strictly, I'm sorry, or equal to on the x equals -2, we'll darken that point. I'm going to go back and make it clear that this was from the red graph that filled in that point. It doesn't matter if you have pencil. It's filled in. Guys, one piece to go. The cubing function produces a graph, right? But only when we're looking to the left of -2. So my cubing function in general, I had key points -2, -8, -1, 1, 0, 0, 1, 1, 2, 8, and it had my snake shape, However, we're only going to darken in where? Only to the left of 2, and it's strictly. So this is going to be an open circle. So this will be an open circle. I don't know if I'm going to be able to do that. Wow. There. That's an open circle. And you see that it's really going steeply down to the left. Solid. That's a nice piecewise-defined function. Why, thank you. All right. The question is, can we go the other direction? Right? Can we go the other direction? So now we're going to go ahead and start with a graph, and we're going to generate the equation. Right? We're going to generate the equation and the piecewise-defined function that would create that graph. So that you guys can match up the different pieces, I'm going to stick with the color coding. And so I'm going to go ahead and first look at that blue portion, and I'm going to write its equation for p of x in blue. That way we can match it up. Everybody, that sure looks like one of my parent functions, right? But only for a particular window. Everybody go ahead and decide with your partner which parent function produces the blue graph and be ready to share. You can look on your green sheet.
Yeah, but like everyone
So which parent function does this look like? Right? Which parent function does this look like? Jackson and Olivia?
Y.
It does. It's exactly y equals x, but only for a particular window. So let's go ahead and write p of x is given by x, but only for the restricted domain when x is to the left of 2. I'm sorry, -2. However, we need to decide if this is going to be a strictly or an or equal to, right? A strictly or an or equal to. Raise your hand if you think you know the answer. Will this be a strictly or an or equal to? Mark?
It'd be a strictly,
How come?
because the dot isn't like filled in.
Absolutely. The function value does not assign the y-coordinate at x equals -2 because this was a strictly. If it were or equal to, then we'd fill in the point because that function would make that y-coordinate when x equals -2. But it only makes it when it's to the left of -2, not at -2. Next piece in red. Go ahead and decide which parent function matches that piece. Although we'll have to do a transformation. Yes, but it could go either one. So long as it's made filled in.
But it can't be both.
Correct. Well, if it's the same one, it end up being okay, but to be safe, we do only one of them. Because we don't want to have two outputs paired with the same input. Okay, ladies and gentlemen, which parent do you want to start with for that middle section in red? Katie and Braden?
Y equals -x.
Wonderful. This looks just like our squaring function, y equals x squared, but it's upside down. So thank you for including a negative. Negative x squared is going to produce the middle section, but only if we're looking in between -2 is less than or equal to x is less than, and we could do or equal to or not. It appears as though both of these pieces fill in the 0, 0. So I can do or equal to here, or I'll leave it strictly because it looks like they've got the black point there. So I'll go ahead and go up until 0. And then I'll do the final piece. Go ahead and decide with your partner what parent function family is going to do the final piece. Everybody find it on your green sheet. So what's the black piece? The black piece. Logan and Barrett, what do you guys think for the black piece?
Square root function.
Raise your hand if you had the same as Logan and Barrett, the square root function. Yes, good job. The square root function, unchanged because it's opening in the same orientation. It has key points 1, 1, and 4, 2. So that's unchanged, square root of x. However, it's only going to apply if we're looking to the right of or equal to 0 because that point's filled in. One of these zeros needs an or equal to. I could have put an or equal to here in red. I could have put an or equal to here in black. But to be safe, we'll only put the or equal to on one. We don't want to run into a situation where we had two filled in points on top of each other because then that would not be a function. We'd have two different filled in circles, right? Two different y coordinates assigned to the same input if these didn't match up. And so we're going to only put the or equal to on one of those domain restriction zeros. Awesome work, you guys. What questions do you have about this one? All right, let's go ahead and do our closure then. So to write and or graph a piecewise function, you must have two things. So we need two different things. You can check back if you need to. I want a written response for everybody. I'll be circulating throughout the room. And lastly, how can you tell which piece of a graph needs an open versus closed circle? And I will ask that you share that. Awesome. Let's go ahead and share your response then with the whole class when I call on you. So please be ready to share your closure responses. To write and or graph a piecewise function, you must have two different things. Right? What's the first thing that we need? Aaron?
The equation of each curve.
Good. We need the equation of each piece, the equation of each curve or each piece. That's my what, right? And the second thing we need, Braden?
The restrictions of the line.
Yes. The domain restriction for each curve. That is where it applies. The window of x values which that piece is graphed upon. We'll call that the where. Window of x values for which that function rule applies. Nice job. How can you tell which piece of a graph needs an open versus a closed circle? Casey?
Without the equal sign, it's open because it's a specific value.
Good. So a strictly inequality symbol without the or equal to will give us an open circle, right? An open circle where we don't fill in versus closed. Casey, did you say?
It's the greater than or less than.
Good. That's the or equal to, the or equal to. Raise your hand if you had the last one, open versus closed. You have that? Awesome. You guys are doing great. So what we're going to do today is go ahead and start the worksheet together. We're going to start the worksheet together. So everybody find the first worksheet. You got two worksheets today. One of them is functions practice worksheet, and one of them is piecewise-defined. Both of them are part of your assignment number 9. So everybody look up at the agenda. Assignment number 9 includes two worksheets. So I put a little ×2 there. So on your purple sheet, it just said the piecewise-defined functions worksheet. We needed more practice with our basic functions, so we made a day 9 function practice worksheet as well. So there's two worksheets for next class. That's why I put a little ×2. Everybody, let's start the worksheet together. So it looks like this first piece in blue, looks a lot like the identity function. And so I could rewrite this as a linear function, but it has a negative slope. So it looks like negative x, but only if I'm looking to the left of or equal to -2. You could make that strictly, so long as you then filled in the domain restriction at -2 on the next piece, a horizontal line, a constant function. It looks like the y coordinates of that piece are 2, everywhere along that middle green piece. And that's only going to apply in between -2 is less than x is less than or equal to +2. And then I'm back to a positively sloped line that goes to the origin at a 45-degree angle. That must be my identity function. I could write that as x, but only when x is to the right of 2. Because I've done or equal to on -2, I'll keep it strictly. Because I've done or equal to on +2, I'll keep it strictly here, but I could have easily flipped those. This could have been red or equal to and then strictly green. This could have been green or equal to and then strictly blue. You just want to make sure you're only doing it to one on each boundary point. What question do you have on the first one? Okay, go ahead and try the second one with your partner. Go ahead and try number 2 with your partner. The tick marks are by ones. It's just 2 pieces, guys. Just 2 pieces.
If it looks like they're connected, then it's
Okay. At this time, I'm going to ask that you pause and share your function rule for each piece. Everybody look at the green piece. Green piece. What function rule did you use for the green piece then? Carson?
We have already that one.
For the green parent function? No? X squared. We don't need the domain restriction yet, just the parent function. Absolutely good. Raise your hand if you had x squared for green. Good. What did you get for the blue piece? Everybody look. What did you get for the blue piece's equation? What did you use for that? Luke?
-x.
-x. Raise your hand if you had -x for the blue. Awesome. So what I meant this to be is tick marks were all y1s, so this is supposed to be 1, right? So we need our domain restrictions. And because there are only 2 pieces, we won't have to do a string like this. we can do each of them with a single X statement. So I'm gonna go ahead and get you started, X, X, and raise your hand if you're feeling confident about your domain restriction. Feeling good about the or equal to's? All right, let's see what you have. Taylor?
X is less than or equal to
And?
X is greater than
Nice job with the strictly versus or equal. Everybody take a look. Taylor's denoted that my green x squared only applies to the left of or equal to x equals 1. And then the blue negatively sloped line only applies when x is to the right of 1, and it's strictly because it's open circle. What questions do you guys have about the start of your piecewise-defined worksheet? Then you have this, and you have the functions practice worksheet. Please write the letter. It looks kind of like last class for day 8, but it's a day 9 functions practice worksheet. 2 things for your assignment. Great work today. You may continue working with your partner. We've got a nice chunk of time, about 15 minutes. I'm going to pause the recording and save it onto YouTube. Oh, a file drill at 9:40, so we still have 9 minutes then.